Hi everyone. Last time we covered the differences between the crystalline and the amorphous materials, symmetry operations, crystal structures, and Bravais lattices. You can find the link for that video in the video description below. Today, we will keep talking about the structural properties of materials, and we will cover the unit cell, the crystallographic points, directions, and planes. Let's start. Translational symmetry leads to the long-range order in the crystalline materials by repeating itself throughout the structure. The smallest repeating unit in the crystal structure is called a unit cell. To further clarify unit cell conceptually, let's use an analogy. Let's think of a single unit cell as a family. Each member of this family represents an atom in the unit cell. And when these families come together in an ordered fashion, they form a society, which is the analogical equivalent of crystal structure of the material. In this system, the family, in other words the unit cell, is the smallest repeating unit in the crystal structure, or in the society. You might have already guessed it, but I would like to articulate that the Bravais lattices that we have mentioned in the previous video also represent the unit cells for crystalline materials. Although knowing the smallest repeating unit and the resulting structure gives an immense amount of information about the materials, sometimes we need more information about the positions and the organization of the atoms in a unit cell. Then, we need to employ Cartesian coordinates to define the crystallographic points, directions, and planes. For this video, the lower left back corner of the unit cell is designated as the origin, and the rest of the points, directions, and planes are defined with respect to the origin on the Cartesian coordinate system. Unlike in mathematical representations, for any negative coordinate value, the minus sign is put above the number rather than before it when representing crystallographic coordinates. The corner designated as the origin is labeled as the 0, 0, 0 point. The lengths of A, B, and C dimensions of a unit cell are taken as equal to 1. So that the point located at the diagonal opposite of the origin has the coordinate values of 1, 1, 1. Then the center of the unit cell would be 1 over 2, 1 over 2, 1 over 2, since the volumetric center is in the middle of the unit cell in all three dimensions. The crystallographic point coordinates find their use when we are to denote the locations of the atoms in a unit cell. In addition to the zero-dimensional point coordinates, there are one-dimensional directions and two-dimensional planes. In order to denote the directions, we use vectors, where we define a beginning and a final point. The vector for the crystallographic directions are defined with respect to the origin point. In other words, the vectors start from the origin and reach a final point. Since all of the crystallographic directions are defined with respect to the origin point, only knowing the coordinates of the final point is all we need for defining a vector for a crystallographic direction. Crystallographic directions are shown using square brackets to distinguish them from the crystallographic point representations. When representing the crystallographic directions, traditionally, the vector is shown in one unit cell. For instance, if we are to show the vector for 1, 2, 3 crystallographic direction, to fit the vector in a single unit cell, we normalize all the given coordinate values with respect to the highest value among them, which is 3 for this case. Then the resulting values, which are 0.33, 0.67, and 1, will be the coordinates of the points where the vector will reach. If we were to show a vector having 0 for any one of the x, y, or z axes, then the vector will be perpendicular to the axis having the 0 value. Let's show 0, 2, 3 vector in a unit cell. As we normalize the values with respect to 3, our vector's final point will be 0, 0.67, and 1. A vector also may have negative values in one or more axes. In that case, the vector is reversed over the axis with the negative value. For instance, the 1, 1, 1 vector would be shown from the origin to the opposite corner along the body diagonal of the unit cell. However, if it was -1, -1, -1, then it would again show the same distance, but the direction would be reversed in all three axes. Or if it was 1, -1, 1, then it would still have the same length, but it would be reversed only over the y-axis. Crystallographic directions are mainly used for defining the growth or deformation directions of the crystalline materials. After covering the crystallographic points and direction coordinates and their representation, next in line is crystallographic planes. Crystallographic planes are of significant importance for powder X-ray diffraction analysis, as the phase analysis of the materials are conducted using the diffraction peaks coming from the crystallographic planes. Crystallographic planes are denoted by Miller indices, which are shown between parentheses, and instead of x, y, and z, h, k, and l are used for representing these coordinates. The given Miller indices represent a crystallographic plane in a crystal structure, but the representation of these planes in a unit cell is a little bit different than that of the crystallographic directions. When you have Miller indices of h, k, and l, this plane will cut the x, y, and z axis on 1 over h, 1 over k, and 1 over l points, respectively. So, as a sanity check, if you have a larger Miller index for an axis, you would expect the plane to intercept that axis closer to the origin than the other two, or vice versa. Let's show the 1, 2, 3 plane in a unit cell. X, y, and z axis will be intercepted at 1, 0.5, and 0.33 points, respectively. But you may be asking yourself, what if I have Miller indices having a zero value for any of the axes? Then what am I gonna do? Let's assume we are given the 2, 1, 0 plane. This plane is expected to intercept the x-axis at 1 over 2, which is equal to 0.5, y-axis at 1 over 1, which is equal to 1, and z-axis at 1 over 0, which is mathematically undefined. Here we will take advantage of the limit function, where the limit of 1 over x when x is going to 0 will be converging to infinity, which means that the crystallographic plane for 2, 1, 0 does not intercept the z-axis at any point in the Cartesian space. Before wrapping up this video, we will mention one specific case for cubic structures. In a cubic structure, a crystallographic direction and plane with the same indices will be perpendicular to each other. This is a very special case, only seen for the cubic crystal system due to its dimensional and angular properties. With that said, we have reached the end of this video. Today, we have talked about the unit cell, the crystallographic points, directions, and planes. In the upcoming video, we will keep talking about the structural properties of materials, and we will cover the point, linear, and planar crystal defects. Until next time.